Today we will discuss about the epitaxial process. In IC fabrication, the first step is the crystal growth and the second one is the epitaxial process. It is a process used to grow a thin crystalline layer on crystalline substrate. And in epitaxial process, the substrate wafer act as a seed crystal. There is a difference between epitaxial and seeded process because in epitaxial process a crystal can be grown below melting point. The epitaxial process used two techniques. The first one is CVD and the second one is MBE. CVD is a chemical vapor deposition technique and MBE is molecular beam epitaxy. Molecular beam epitaxy use evaporation method. Epitaxial process is of two types. First is the homoepitaxy and the second one is the heteroepitaxy. In homoepitaxy, the crystalline layer and the substrate is of same material. For example, silicon grown on silicon. In heteroepitaxy, the substrate and the layer are of different material. For example, aluminum, gallium arsenide, arsenic on gallium arsenic. The another example of heteroepitaxy process is SOS, silicon on sapphire. SOS is silicon on sapphire. Sapphire is aluminum oxide. Aluminum oxide has a hexagonal lattice pattern and silicon has a diamond lattice structure. So SOS is two similar materials, silicon and sapphire, dissimilar materials, silicon and sapphire, grow one on top of another. So there are three cardinal rules for or during heteroepitaxy. Those three cardinal rules are: number one, the heteroepitaxial process is possible if only there is no chemical reaction between substrate and the epitaxial layer. The second rule is there should not be any lattice mismatch. And the third, the coefficient of thermal expansion should be matched. So three cardinal rules for heteroepitaxial process. The first one is no chemical reaction between substrate and epitaxial layer, and there should not be a lattice mismatch, and coefficient of thermal expansion should be matched. But only the first rule, that is no chemical reaction between substrate and epitaxial layer, must be strictly followed. And because if there is a chemical reaction between the two materials, we cannot grow a epitaxial layer. And the second rule, lattice mismatch and thermal expansion, coefficient of thermal expansion can be tolerated up to a certain level. Just like in the above example, we discussed about SOS and we told that sapphire means aluminum oxide is a hexagonal lattice pattern and silicon is a diamond-like pattern or diamond-like crystal. And there is no lattice mismatch, but it can be grown. The thickness of the layer will be the problem, and that is we can see when there is a lattice mismatch, there will be a lot of strain in the epitaxial layer. So up to a certain thickness, this strain can be taken or this strain can be tolerated. Beyond that, it is not allowed. The another example of heteroepitaxy is aluminum gallium arsenide on gallium arsenide. In this case, we have a perfect lattice matching. Silicon epitaxy was developed to enhance the performance of BZT, discrete bipolar transistor, The bipolar transistors were first fabricated in bulk wafer using the wafer resistivity to determine the breakdown voltage of collector, but the higher breakdown voltage need high resistivity material, and this required, coupled with the thickness of wafer, result in excessive collector resistance that limit high frequency response and increase power dissipation. So epitaxial growth of a high resistivity layer on a low resistivity substrate solve this problem. Bipolar integrated circuit utilize epitaxial structure in the same way as discrete transistor utilize it. The substrate and epitaxial layer have opposite doping types to provide isolation, and a heavily doped buried layer or diffusion layer served as a low resistance collector contact. Unipolar devices such as FET and VMOS technology uses epitaxial wafer. Epitaxial structure Epitaxial structure used to improve the performance of DRAM and CMOS IC. In DRAM and CMOS circuit, device could be fabricated in bulk wafer, but certain circuit parameters are optimized using epitaxial material. Epitaxial wafer have two fundamental advantages over bulk wafer. Epitaxial layer on a substrate often containing one or more buried layer, so it offers designer a more control on doping profile in device that available with diffusion or ion implantation. The second advantage of epitaxial layer is the physical property of epitaxial layer differ from those of bulk material. For example, epitaxial layer are generally oxygen and carbon free, which is not generally obtained with the melt grown silicon.